Ever wonder why modern race cars don't have real glass windows? The answer traces back to one mechanic who looked at a NASCAR stock car and saw weight where everyone else saw necessity. Smokey Yunick didn't just break the rules. He rewrote the engineering playbook of American motorsports by replacing every piece of glass in his race cars with something called Lexan. That simple swap dropped 75 pounds from his cars overnight. In racing, where victories are measured in thousandths of seconds, that weight reduction was like finding free horsepower hidden in plain sight. Picture this. It's 1968 at Daytona International Speedway. The garage area buzzes with the sound of impact wrenches and revving engines. Team after team rolls out their meticulously prepared stock cars, each one carrying thick safety glass in every window opening, windshield, rear window, side windows if they hadn't been removed. Standard procedure, NASCAR regulations, the way it had always been done. But in one corner of the garage, behind closed doors, Smokey Yunick and his crew were carefully installing sheets of clear plastic where glass should have been. They were about to change racing forever. This is the story of how one mechanic's obsession with weight reduction revolutionized not just NASCAR, but every form of motorsports from Formula One to drag racing. It's about a material so revolutionary that it went from classified military applications to becoming the standard in every professional race car on Earth. And it all started because Smokey Yunick refused to accept that glass was the only option. To understand why Yunick's Lexan windows were so revolutionary, we need to travel back to the golden age of stock car racing. The late 1960s were a different world. NASCAR's rulebook was thinner than a diner menu. Stock cars were still loosely based on actual production vehicles you could buy from a dealership. Teams were run out of converted gas stations and backyard garages. The sport hadn't yet evolved into the multi-billion-dollar precision operation it is today. The cars themselves were brutally simple by modern standards. Big block V8 engines producing around 500 horsepower, 4-speed manual transmissions, solid rear axles, drum brakes that would fade after 10 hard laps. No power steering, drivers needed forearms like steel cables just to turn the wheel. These were 3,400-pound missiles barely controlled by technology that belonged in the 1950s. But here's where it gets interesting. In 1968, aerodynamics was becoming the new frontier in NASCAR. The Ford Torino Talladega and Mercury Cyclone Spoiler II were about to usher in the aero wars. Dodge was developing the infamous Charger Daytona with its massive rear wing. Plymouth would soon follow with the Superbird. Teams were discovering that the shape of the car mattered as much as what was under the hood. And with aerodynamics came a newfound obsession with weight. Every pound removed from a race car pays dividends everywhere on the track. It accelerates faster, it brakes shorter, it changes direction quicker. It puts less stress on tires, allowing them to last longer while maintaining grip. In racing terms, weight is the enemy of speed. Engineers have a saying, adding power makes you faster on the straights. Removing weight makes you faster everywhere. The problem was that NASCAR's rulebook required certain components to remain stock, or at least stock appearing. Windows were one of those components. The sanctioning body wanted race cars to look like the vehicles fans drove to the track, maintaining that crucial marketing connection between Sunday's winner and Monday's showroom sales. A stock car without proper windows wouldn't look like a stock car at all. Standard automotive glass in 1968 was heavy, really heavy. A typical windshield weighed 25 to 30 pounds. The rear window added another 20 to 25 pounds. Side windows, if retained, contributed 10 pounds each. Door vent windows, remember those little triangular pieces, added another 5 pounds per side. All told, the glass in a stock car could easily exceed 75 pounds. That's the equivalent of carrying an extra pit crew member around the track for 500 miles. Smokey Yunick looked at all that glass and saw dead weight. But more than that, He saw an opportunity that everyone else was missing. While other crew chiefs were drilling holes in brake pedals to save ounces, Yunick was thinking about pounds. Lots of pounds. He just needed the right material to replace the glass. Enter Lexan, a polycarbonate resin developed by General Electric in 1953. The material's origin story reads like something from a spy novel. Initially developed for military applications, Lexan was used in fighter jet canopies, astronaut helmets, and bulletproof barriers. It was 250 times stronger than glass, but weighed half as much. It could be bent, molded, and shaped without breaking. It was optically clear, UV-resistant, and could withstand impacts that would shatter traditional glass into thousands of pieces. The aerospace industry had been using Lexan for years. The Apollo spacecraft's windows were made from it. Military helicopters used it for their bubble canopies. But nobody in NASCAR was thinking about space-age materials. They were still using technology from the 1940s and calling it cutting edge. Nobody except Smokey Yunick. Now here's the thing about Smokey Yunick. He wasn't just a mechanic. He was an engineer without the degree, an inventor who held dozens of patents, and arguably the most creative rule bender in the history of motorsports. His garage in Daytona Beach, Florida, was less a race shop and more a laboratory where the boundaries of what was possible were constantly being tested. He once built a 7/8 scale Chevelle that looked perfect to the naked eye, but was smaller in every dimension, making it more aerodynamic. He invented the extended fuel line that added 5 gallons of capacity by routing it through the entire car. He figured out how to inflate a basketball inside a fuel tank after inspection to displace volume and create room for more gas. Yunick's approach to racing was simple. The rule book told you what you couldn't do, not what you could do. And if the rule book didn't specifically prohibit something, it was fair game. Glass windows? The rule book said the car needed windows. It didn't say what material those windows had to be made from. The first challenge was sourcing the Lexan. In 1968, you couldn't just order sheets of aircraft-grade polycarbonate from a catalog. This was specialized material with limited civilian applications. Yunick had to leverage his connections in the aerospace industry, calling in favors from engineers he'd met through his various consulting projects. The material itself was expensive, nearly 10 times the cost of glass by square foot. But in racing, cost is relative to performance gained. The installation process required completely different techniques than glass. Lexan could be cut with a fine-tooth saw, but the edges had to be flame-polished to prevent stress cracks. It expanded and contracted at different rates than the steel body, requiring special mounting techniques with rubber gaskets and oversized holes to allow for thermal movement. Too tight, and the Lexan would buckle in the heat. Too loose, and it would rattle itself to destruction from vibration. Yunick and his team spent weeks perfecting the installation process. They discovered that Lexan scratched more easily than glass, requiring protective film during installation and careful handling. They learned that certain cleaning chemicals would cloud the material permanently. They found that while Lexan was incredibly strong against impact, it could be damaged by prolonged exposure to certain fuels and lubricants common in a race garage. But the real revelation came when they put the car on the scales. The weight savings were even better than calculated. Not only was the Lexan itself lighter, but the mounting hardware could be simplified. Glass required heavy-duty frames and thick rubber seals to prevent shattering. Lexan could be secured with aluminum frames and lightweight fasteners. The total weight reduction approached 75 pounds. In racing terms, an absolute goldmine. The performance gains were immediate and measurable. Acceleration improved by 0.2 of a second from 0 to 60 mph. That might not sound like much, but over the course of a 500-mile race with dozens of restarts and acceleration zones out of corners, those tenths add up to seconds, and seconds add up to positions. Braking distances shortened by several feet from 150 meters to Marfort. The car changed direction more eagerly, responding to steering inputs with less inertia, fighting against the driver's intentions. But the benefits went beyond simple weight reduction. The lower center of gravity, most of the glass weight was high on the car, improved handling balance. The reduced weight on the suspension components allowed the springs and shocks to work more effectively, keeping the tires in better contact with the track surface. Tire wear improved because there was less mass pushing down on them through corners. Even fuel mileage increased slightly, as the engine didn't have to work as hard to accelerate the lighter car. The first race where Yunick's Lexan-Windowed car appeared was like bringing a gun to a knife fight. Competitors noticed something was different but couldn't quite place it. The car looked normal from a distance. It was only up close that the difference became apparent. The windows had a slightly different optical quality, a subtle waviness that glass didn't possess. They flexed slightly when pushed. They sounded different when tapped. NASCAR officials were caught completely off guard. Nothing in the rulebook prohibited plastic windows. The rules specified minimum window openings, required windows to be transparent, and mandated certain safety standards. Yunick's Lexan met all these requirements. In fact, it exceeded them. Lexan was actually safer than glass in many crash scenarios, as it wouldn't shatter into dangerous shards. The racing community's reaction was swift and predictable. Half the garage cried foul, claiming Yunick had gone too far this time. The other half immediately started sourcing their own Lexan supplies. Within weeks, plastic windows began appearing throughout the NASCAR paddock. Teams that had been struggling for speed suddenly found it. The competitive balance shifted overnight. Consider the physics involved. In a 500-mile race at Daytona, a car might accelerate from low speed to racing speed over 200 times, out of pit stops, after cautions, exiting corners. Each acceleration requires force equal to mass times acceleration. With 75 fewer pounds to accelerate, the same engine power produces more acceleration. It's basic physics. But the cumulative effect over a race distance was profound. The cornering gains were equally significant. Centripetal force in a corner equals mass times velocity squared, divided by radius. Less mass means less force, trying to push the car off its intended line. The tires don't have to work as hard to generate lateral grip. The suspension doesn't have to control as much weight transfer. Everything about the car's dynamic behavior improves. Let me put that in perspective. Removing 75 pounds from a 3,400-pound race car is a 2.2% weight reduction. That might not sound like much, but in racing, teams spend millions of dollars chasing single percentage point improvements. Yunick achieved it with a few $100s worth of plastic and some creative thinking. The Lexan windows also had unexpected benefits that only became apparent over time. Unlike glass, Lexan could be formed into complex curves, allowing for better aerodynamics. The rear window could be shaped to reduce drag without the limitations of flat glass. Side windows could be curved to smooth airflow along the body. It was another advantage that compounded with the weight savings. Visibility improved too. Lexan didn't require the thick frames that glass needed for safety. The window openings could be larger, giving drivers better sight lines. In the chaos of pack racing, being able to see that extra few inches to your side could mean the difference between avoiding a wreck and becoming part of it. But not everything about Lexan was superior. The material had its drawbacks, and teams learned about them the hard way. Lexan scratched easily, much more easily than glass. A careless crew member with a belt buckle could leave permanent marks. Cleaning required special techniques and products. Normal glass cleaner could cause hazing. Paper towels could create micro scratches that accumulated into visibility problems. Heat was another issue. Lexan has a lower melting point than glass. In the extreme temperatures of a race car interior, which could exceed 140 degrees Fahrenheit, Lexan could deform if not properly supported. Teams learned to add additional bracing in strategic locations to prevent the windows from bowing outward at speed. The material also had different optical properties than glass. While perfectly clear when new, Lexan could develop a yellowish tint over time from UV exposure. It could distort slightly under stress, creating visual aberrations that some drivers found disorienting. These weren't deal breakers, but they required adaptation and management. NASCAR's response to the Lexan revolution was measured but inevitable. By the 1970 season, the rulebook had been updated. Lexan windows were explicitly approved for competition, but with specifications. Minimum thicknesses were mandated for safety. Certain areas, like the windshield, required specific grades of polycarbonate. Installation methods were standardized to ensure the windows would perform predictably in crashes. The sanctioning body recognized that Lexan actually improved safety in many scenarios. In a rollover, Lexan would flex and absorb energy rather than shattering. In a side impact, it would deform but remain intact, maintaining the structural integrity of the window opening. For drivers, this meant better protection. For NASCAR, it meant fewer injuries and better optics for the sport. The adoption of Lexan windows spread beyond NASCAR like wildfire. IndyCar teams, who were always pushing the boundaries of weight reduction, immediately saw the potential. Formula One, despite its reputation for being slow to adopt outside innovations, began experimenting with polycarbonate windows by the early 1970s. Drag racers, where every pound directly correlates to elapsed time, made the switch almost overnight. Even production car manufacturers took notice. High-performance road cars began incorporating Lexan rear windows and fixed side windows as weight-saving options. The Ferrari F40, one of the most iconic supercars ever built, famously used Lexan windows to keep weight down. Porsche offered Lexan windows as part of their lightweight packages for track-focused models. What started in Smokey Yunick's garage had influenced the entire automotive industry. The economic impact was substantial too. A cottage industry emerged around racing-specific Lexan applications. Companies specialized in forming, coating, and installing polycarbonate windows for race teams. New grades of material were developed specifically for motorsports, with improved UV resistance, better optical clarity, and enhanced impact resistance. The technology that trickled down from aerospace to racing was now driving innovation in material science. By the mid-1970s, you couldn't find a serious race car anywhere in the world still using glass windows where Lexan was permitted. The weight savings were simply too significant to ignore. Teams that resisted the change found themselves at an insurmountable disadvantage. It had become as fundamental to race car construction as roll cages and racing slicks. The numbers tell the story best. A modern NASCAR Cup Series car uses approximately 15 square feet of Lexan windows, at a thickness of 0.236 inches for the windshield and 0.177 inches for other windows. The total weight of all windows is about 25 pounds. The equivalent glass would weigh nearly 100 pounds. Over a 36-race season, traveling hundreds of thousands of racing miles, that 75-pound difference translates to measurable gains in performance, tire life, fuel economy, and component longevity. Think about the butterfly effect of Yunick's innovation. Every race team in the world now uses lightweight windows. That technology has saved millions of pounds of weight over millions of racing miles. It's improved safety for thousands of drivers. It's influenced the design of countless production vehicles, all because one mechanic in Daytona Beach looked at a window and asked, "Why does this have to be glass?" The Lexan window innovation also exemplified Yunick's broader philosophy about racing development. He understood that the biggest gains often came from questioning fundamental assumptions. While other teams were optimizing within accepted parameters, Yunick was challenging the parameters themselves. Why did windows have to be glass? Why did fuel tanks have to be a certain size? Why did cars have to be the dimensions Detroit specified? This thinking influenced a generation of race engineers and crew chiefs. Ray Evernham, Chad Knaus, and other modern NASCAR crew chief legends cite Yunick as an inspiration. His approach, looking for advantages in places others weren't even considering, became the template for innovative thinking in motorsports. The Lexan-Windows were just one example of hundreds of innovations that emerged from this mindset. Modern racing continues to build on Yunick's foundation. Today's Lexan-Windows are dramatically more advanced than what was available in 1968. Multi-layer constructions provide better impact resistance. Anti-reflective coatings improve visibility. Heated elements prevent fogging. Tear-off films allow instant cleaning during races. The basic concept remains the same: lightweight, strong, safe, but the execution has evolved with technology. The latest development is the integration of heads-up display technology into Lexan windshields. Imagine Yunick's reaction to learning that the plastic windows he pioneered now display real-time telemetry data directly in the driver's field of view. Speed, RPM, fuel levels, tire temperatures, all projected onto the same material that started as a simple weight-saving measure. NASCAR's next-gen car, introduced in 2022, features a Lexan windshield that's actually part of the car's structural integrity. It's bonded to the chassis and helps transfer loads in a crash. The material that Yunick smuggled into the sport as a loophole has become so fundamental that the cars are now designed around it. That's the ultimate validation of an innovation, when it becomes so essential that you can't imagine the sport without it. The environmental impact deserves consideration too. Lexan windows can be recycled, unlike laminated safety glass, which often ends up in landfills. They last longer than glass in racing applications, requiring less frequent replacement. The reduced weight means less fuel consumption over the life of the race car. Even from a sustainability perspective, Yunick's innovation was ahead of its time. But perhaps the most important legacy of the Lexan window revolution is what it represents about innovation itself. Smokey Yunick didn't have a massive corporate R&D budget. He didn't have computer simulations or wind tunnels. He had curiosity, creativity, and the courage to try something different. He saw an inefficiency that everyone else accepted as inevitable and refused to accept it. The story also highlights the importance of cross-pollination between industries. Lexan existed for 15 years before Yunick brought it to NASCAR. It was already proven in aerospace and military applications. The innovation wasn't in inventing the material, it was in recognizing its potential in a completely different context. How many other aerospace technologies could revolutionize racing? How many racing innovations could benefit aerospace? The boundaries between industries are often more permeable than we think. Consider the mindset required to make that leap. In 1968, suggesting plastic windows for a race car would have seemed absurd to most people. Windows were glass. They had always been glass. They would always be glass. It took someone willing to be laughed at, willing to fail, willing to challenge conventional wisdom to break that paradigm. That's the essence of innovation, not just having ideas, but having the conviction to pursue them when everyone thinks you're crazy. The resistance Yunick faced was predictable. Innovation always threatens the established order. Teams that had optimized their cars around traditional glass windows suddenly found their advantages nullified. Suppliers who provided automotive glass to race teams saw their market disappear. Officials who were comfortable with existing rules had to adapt to new technologies. Change is uncomfortable, even when it's clearly beneficial. But ultimately, performance wins arguments in racing. The stopwatch doesn't care about tradition or convention. Lap times are the ultimate arbiter of innovation, and Yunick's Lexan-Windows delivered undeniable performance advantages that no amount of resistance could overcome. Within 2 years, what had been revolutionary became mandatory. Teams that didn't adopt Lexan-Windows simply couldn't compete. This pattern repeats throughout racing history. Rear wings were controversial until they became essential. Radial tires were resisted until their superiority was undeniable. Carbon fiber was too exotic until it wasn't. Each innovation follows the same trajectory: ridicule, resistance, reluctant acceptance, universal adoption, then amazement that anyone ever did it differently. The financial implications were substantial. That initial investment in expensive Lexan sheets probably cost Yunick a few $1,000s, serious money in 1968. But the performance advantage it provided was worth hundreds of thousands in prize money and sponsorship value. More importantly, it established Yunick's reputation as an innovator, attracting drivers and sponsors who wanted to be associated with cutting-edge technology. For the broader industry, the Lexan revolution created entirely new market segments. Companies that had never considered motorsports as customers suddenly found race teams beating down their doors. Materials scientists who had worked exclusively on military projects were now consulting for NASCAR teams. The flow of knowledge and technology between industries accelerated, benefiting everyone involved. Today, when you watch any form of motorsport, NASCAR, Formula One, IndyCar, sports cars, drag racing, you're seeing Smokey Yunick's legacy. Every one of those cars uses polycarbonate windows. It's so universal that most fans don't even know there was a time when race cars used actual glass. What was once a clever hack by a rebellious mechanic has become as fundamental to racing as engines and tires. The philosophy behind the innovation matters as much as the innovation itself. Yunick didn't just save weight. He demonstrated that sacred cows could be slaughtered, that "we've always done it this way" is never a good enough reason, that innovation can come from unexpected places. He showed that one person with a different perspective could change an entire industry. Modern race teams spend millions on computational fluid dynamics, finite element analysis, and 7-post rigs. They have materials scientists and aerodynamicists on staff. They test in wind tunnels that cost more than Yunick's entire career earnings. Yet, for all that technology and expertise, they're still chasing the same goal Yunick pursued with Lexan-Windows: finding free speed in unexpected places. The human element of this story shouldn't be overlooked. Smokey Yunick was a character in every sense of the word. 6 feet tall, perpetually wearing a cowboy hat, chain-smoking cigarettes, even while working on fuel systems. He was brilliant but irascible, innovative but stubborn, respected but controversial. He didn't just bend rules, he twisted them into pretzels and dared officials to do something about it. His Lexan-Windows were just one chapter in a career full of innovations, controversies, and legendary stories. He was banned from NASCAR multiple times. He told officials where they could stick their rulebook. He built hot rods that went 300 mph at Bonneville. He invented a new type of internal combustion engine. He consulted for General Motors while simultaneously cheating with their cars in ways that made GM engineers both furious and admiring. Yet, despite all his other achievements, the Lexan-Window innovation might be his most lasting legacy. It's the one that every race car in the world still uses. It's the one that saved lives by eliminating flying glass in crashes. It's the one that proved weight reduction could come from reimagining fundamental components, not just drilling holes and using thinner metal. The next time you watch a race, take a moment to look at those windows. They might appear unremarkable, just clear panels keeping the wind out. But they represent something bigger: the power of questioning assumptions, the value of cross-industry innovation, the impact one creative individual can have on an entire sport. They're monuments to ingenuity, testaments to the idea that innovation doesn't always require million-dollar budgets and corporate backing. Sometimes it just takes someone willing to ask, why not plastic? So here's a question for you. What's the modern equivalent of glass windows in racing? What accepted component or method is everyone using simply because that's how it's always been done? What would Smokey Yunick be experimenting with if he were still in that Daytona Beach garage today? Drop your thoughts in the comments below, because somewhere out there, the next game-changing innovation is waiting for someone bold enough to try it. And if racing history teaches us anything, it's that the biggest breakthroughs often come from the simplest questions. Until next time, keep questioning everything, and remember, in racing, as in life, the heaviest burden is often the one we never thought to put down.